Okay, we're going to discuss section 8.3, geometrically defined vectors and applications. I'm going to just sort of read through the textbook. There's terminology that we have to get used to here. Concepts themselves are not that difficult. We just have to get used to the new terminology. So we're going to just read together. Quantities that involve magnitudes, and I hope you can see that. Let me zoom in a little bit for you. Okay, quantities that involve magnitudes, such as 45 pounds or 60 miles per hour, can be represented by real numbers called scalars. Okay, so you can think of magnitude as a force. So force, of course, might be, for example, the wind blowing at a certain force, or pounds could be a force, so maybe you've got something pulling on something else. Other quantities, called vector quantities, involve both magnitude and direction. Typical vector quantities are velocity, acceleration, and force. For example, traveling 50 miles per hour east represents a vector quantity because it's got both a force and a direction. A vector quantity can be represented with a directed line segment, a segment that uses an arrowhead to indicate direction, called a vector. There is a video that I may post on Blackboard that I watched it and I thought it gave a helpful explanation of what a vector is, because it is an abstract concept and you might struggle with that a little bit. So I will have a YouTube video posted that I didn't make myself, but I thought it was a pretty good, helpful illustration of what a vector means. So just continuing to read, the length of the vector represents the magnitude of the vector quantity. Okay, so in other words, looking at this, it looks like a ray, but it's a line segment that's got an arrow on one end. The length of it represents the magnitude, or the force, how powerful it is. The direction of the vector, indicated by the arrowhead, represents the direction of the quantity. Alright, so for example, it could be going northeast or southwest. Alright, so we've got pictures of vectors here. We're not going to read everything, but I am going to continue to read at the bottom of the page. Let's try to get this where it'll show up. Okay, when we indicate vectors in print, it is customary to use boldface type or an arrow over the letter or letters. Thus, OP and OP with the arrow over it both represent the vector OP. When two letters name a vector, the first indicates the initial point and the second is the terminal point of the vector. Knowing these points gives the direction of the vector. For example, vectors OP and PO, which we had up here, that's OP and PO, are not the same vector because they go in opposite directions. They have the same magnitude but opposite directions. So the magnitude of vector OP is written like this. It looks like absolute value bars surrounding the OP. That represents magnitude. I'd like to look at some examples with you, and forgive the crinkliness of my page. My textbook got wet. So the first question, we're asked to name all pairs of vectors that appear to be equal. So we're looking at these over here. So remember, in order for these to be equal, two things need to happen. They have to be pointing in the same direction, and they also have to be the same length. Okay? If you find a pair that are parallel, that's a very helpful indication that you might have equal vectors. They would also have to be pointed in the same direction. So if we look at M, you can see it's pointed, it's pointing up, N is pointing up. I don't know how well this is going to show up on your screen. O points up. So M, N, O, all of these vectors point up. And then we have vectors P and Q. P points up and Q points down. So even though these are parallel, they're not equal because they go in opposite directions. R and S, R points up, S points down, and then T points to the right. So looking for vectors that appear to be equal, they have to, if you think of it in terms of slope, the slopes would have to be the same to the best that you can tell by just looking at it. And they also have to go in the same direction. So I think vector M and vector P Notice those are parallel, and they also both point in the same direction. So M and P appear to be equal. Vector N here and vector R, they are parallel. They appear to be the same length, and they also both point in the same direction. So these appear to be equal, vector N and vector R. Number 2, name all pairs of vectors that are opposites. Okay, your vectors are opposites if they are parallel and they're the same length, but they point in opposite directions. So, for example, vectors P and Q, they would fit that description. They are opposites. P points up, Q points down. They're parallel lines, and they are the same length. I shouldn't say they're parallel. The vectors are, I shouldn't say that they're parallel lines. They're not lines, but the vectors are parallel to each other, and the ray or the segment, the line segments are the same length. They point in opposite directions. So P and Q are opposites. R and S, vector R, vector S, same thing. They're the same length, they're parallel, and they point in opposite directions, so they're also opposites. Is there anything else? Yes. Vector N is also opposite of vector S, but they point in opposite directions, they're parallel, and they're the same length. Vector M and vector Q point in opposite directions, they're parallel, and they're the same length. So vectors M and Q would be opposites. Number 3, name all pairs of vectors where the first is a scalar multiple of the other with the scalar positive. Okay, so what does that mean? You can think of a scalar as a constant. So it just means that whatever that vector length is, we're multiplying that by a positive number. Now it could be a fraction. So the scalar multiple, all it's going to do is it's going to make the vector longer or shorter, or if the vector happens, if the scalar happens to be negative, then it would probably change the slope of it, but we're not going to worry about that right now. So multiplying by a positive scalar is just going to make it shorter or longer. So for example, if we look at vector M and then vector T, they are parallel, they point in the same direction, but it looks like vector T is about half as long as vector M. So it appears that vector T is a scalar multiple of vector M, so for example, you could, maybe vector M is equal to 1/2 times vector T, or perhaps vector T is equal to 2 times vector M. All right. You could also include the ones that we said were equal, because you could just say that scalar is 1. So if you multiplied 1 times M, you'd have scalar 1. So vectors P and M would be scalar multiples of each other as well. Okay, and number 4, we want to name all pairs of vectors where the first is a scalar multiple of the other with the scalar negative. So a negative scalar or a negative constant, the only thing it's going to do is change the direction of the vector. And of course it could make it shorter or longer. For example, vector M and vector Q, okay, they are the same vector except Q is going in the opposite direction. So we would say that M is equal to -1 times Q, so that would be a scalar multiple with our scalar negative. Same thing with R and S. There, this scalar would be -1. All it's doing is changing the direction of the vector. Are there any others? Yeah, vector N and vector S, they're the same, but the directions are different. So that would be a scalar multiple with a negative scalar. Okay, the next thing we want to talk about is what happens if we add vectors. So, and then we're going to refer to vectors A through H below, make a copy or a sketch of each vector, then draw a sketch to represent each of the following. For example, find A plus E by placing A and E so that their initial points coincide. Then use the parallelogram rule to find the resultant as shown in the figure on the right. So I need to explain some stuff here. So I'm going to take, I'm going to look at vector A and vector B. Excuse me, I know you can see that. Okay, so here's vector A and here's vector B. Okay, so basically when we put these things together, they have to stay pointed in the exact same direction. So we can't twist them around without it changing their values. So we keep them just like they are, but we're going to connect their terminal sides. So the terminal side is the side that does not have the arrow. So if we take vector A and vector B and we connect the terminal sides, I'm going to try to draw the picture to the best of my ability, but it's going to look like something like this. So here's vector A, and it should be exactly the same angle that, shoot, there, that's my vector A, and it's the same angle as the one in the book. And my vector B, I'm just going to draw it so that the terminal points touch. So I would draw it like this. So that's vector A, vector B, the terminal sides touch. Okay, so I have tried to draw them as close to what I have in the book as possible. Let me draw it again. I think I can do a better job of that. So they said to trace it, so let's just trace it. So here's A, and then there's B, and I'm just going to put their terminal sides together. So here's B. Okay, that's a little bit better. I traced it directly from the book. So the slopes and the slants, all that need to be exactly the same as the original problem to the best of our ability. Okay, so so this is vector A, this is vector B. And to add these together, what needs to happen is we're going to create a parallelogram. So the length of side A, or vector A rather, we're going to come over here and we're going to sketch that in with a dotted line. And then the length of vector B, we're going to draw a parallel side to vector B over here and create this parallelogram. Alright, the resultant is basically the result when we add the two vectors together. And it will be a new vector that has the same terminal side, so it's got the same beginning place down here, and it ends at the other side of the parallelogram. So this is the vector A plus B. Okay. So what in the world just happened? All right, well, let me explain it one more time. We traced the vectors that we were given and we put their terminal sides so that they touched, so the sides that did not have the arrows. We drew parallel sides that were the same length to create a parallelogram. So with side B, I drew a parallel side over here that had the same exact length as vector B, and then I drew a side that was parallel to vector A, and it was supposed to have the same exact length as vector A. And then the diagonal is the sum A plus B, and we call that the resultant. And then it goes as far as that parallelogram. So the little arrow on the new vector will be at that corner created by that parallelogram. Okay, let's look at another one. Okay, what about number 5? Okay, I know you can't see this, but in number 5, we are asked to, what did they say? Make a copy or a sketch of the vector. Draw a sketch to represent the following. Okay, so in number 5, we're asked to draw a sketch to represent negative B. All right, well, here's B. Negative B is going to go in the opposite direction. So negative B can be drawn. I'm just tracing the original vector, but it's going to go in the opposite direction. So that's negative B. So this was the original B under here, and there's that's negative B. It just gives me the opposite direction. Number 7, I'm asked to find 2C, vector 2 times C. So that's a scalar multiple of 2. Here's vector C. So I'm going to just trace this vector, but the scalar multiple of 2 means that it needs to be twice as long. So I'm just going to do this right through my paper. This is the original length of vector C, but I'm going to just double that. So it's going to look like this, and I put the arrow in the same direction as the original. So 2 times C would look like this. That's just about double the length of the original. Then we're asked to do H plus G. Now, alright, so here's H, that's vector H, that's vector G. So to add these together, I'm going to do, I'm going to first trace, let's do it like this. So I'm going to find, here's vector H, I'm just tracing it through the paper. Okay, and if I do H plus G, that's when we have to make our vectors touch at their terminal side. So here's vector G over here. It goes like this. Terminal side is here, and the arrow is over here. So I'm going to trace this, but I need it to touch vector H. So I'm just going to move my paper over a little bit. I'm trying very hard not to rotate it. And then I can draw vector G here. Okay, so there's vector G. So to do H plus G, I need another parallelogram. So I'm going to draw a side parallel to vector G, like this. And I need a side parallel to vector H. So I'll come over here to the best of my ability. And these parallel sides are always going to be the exact same length as the original vectors. And of course, I know mine's not perfect, but it should be the same length. So this side should be the same length as vector H, and it should be parallel to vector H. This side should be the same length as vector G, and it's parallel to vector G. The diagonal that goes from the terminal sides to the opposite vertex of the parallelogram creates the vector H plus G. So we put the arrow at the corner, and our new vector is H plus G. So that's all. That's how we geometrically show. That's how we draw vector addition. Okay, one more of these we need to look at. Let's look at number 13. This one, I'm going to need to get a little more stuff. So I'm going to pause the video for a moment, and we'll come back and continue in a second with number 13. In number 13, you've got 3 vectors to add. So that's the next thing we're going to do. Okay, in this example, and you're going to have to excuse the noise in the background. I got a little one back there, and he's cranky, so we'll see what happens. So we're doing vector addition, but this time we're adding 3 vectors. So we're going to start by adding order of operations tells us to do B plus C first, and then add that result to vector A. Alright, so to do vectors B plus C, we take these two, alright, we take these two, we connect them at their terminal sides, and so here's C, and here's B. God, he's not feeling well, so he's cranky right now. So B plus C, we draw the parallelogram like we talked about before. Okay, so there's our parallelogram. And then the resultant is B plus C, and the arrow for the new vector goes in the actual corner of the parallelogram. So this is B plus C. Alright, now, so now we have to take the new vector that we just got and add it to A. So I would recommend doing this in a completely separate step. So here's B plus C. We're going to take this one and add it to A. So I'm just going to try to trace my resultant B plus C at the exact same angle to the best of my ability. So it needs to be parallel to what I drew up there. And it needs to be about the same length to the best of our ability. So there's B plus C. And A is up here in the corner. There's A. So we're going to draw this vector. So just imagine just picking it up, but never rotating it, just keeping it in the exact same position and dragging it down here. So we're going to draw it parallel to what we have up here, same length. So it looks about like this. There's A. Okay. And we do the same process that we did before. So we make a new parallelogram. Alright, and then this corner here is going to be where the new vector ends. So the new vector, so this what we've just drawn, is A plus parentheses B plus C. And it's this one here. Okay. It turns out so that if you were to do vector C plus B instead of vector B plus C, that it would give you the same result. And so that means that vector addition is commutative, just like regular addition is. In other words, if you change the order, you'll still get the same result. Okay, so that's how you're going to handle one where you have to do more than one vector. Alright, so you'll have one of these in the homework, definitely. Alright, let's see what else we've got. Okay, so we're going to look at example, this is number 23 in the textbook. I've got to pause the video for a second though. Okay, we're going to do number 23 together. It says, use the parallelogram rule to find the magnitude of the resultant force for the two forces shown in each figure. Round to the nearest tenth. So you've got a vector with magnitude 40 pounds and a vector with magnitude 60 pounds. And the angle formed is 40 degrees. Okay, so they're asking us to find the magnitude of the resultant force. So that just means that we have to find the resultant, which is what you get when you add the two vectors together. And the magnitude is the length of that vector. So we're going to create a parallelogram, and that resultant force will be the diagonal. We have to find the length of our diagonal of the parallelogram. And we can do that using some of the concepts that we've learned earlier in this chapter. Okay, so just redrawing the picture. We've got an angle of, where our first vector was 40 pounds, and our second vector is 60 pounds. And the angle formed by those vectors is 40 degrees. Okay, so we have to find we're going to find the magnitude of the resultant. So we're going to draw a parallelogram. Okay, now of course the opposite lengths of the parallelogram are going to match what we have for the vectors. So we have this side is 40 pounds. We'll just say 40. This side is 60. This angle, excuse me. This is the little boy that's so cranky. He's not feeling well. He wants his shoes to go outside and play, but we can't go outside and play because Mom's got to get these videos done. And he's not happy. Yeah, you're not happy. No. I know. You say bye-bye? Bye-bye. Say bye-bye. Bye. Bye. Okay, so back to problem 23. We drew these are the vectors that were given in the problem. This is the angle that was formed by the vectors. And then we've drawn this parallelogram. Okay, we know that, we're being asked for the magnitude of the resultant, so that's going to be, the resultant is going to be the sum of these vectors, which we know is going to go from their terminal side all the way to the far corner of the parallelogram, which is simply the diagonal of the parallelogram. Okay, so I'm going to call this x because that's what we're solving for. And to do this, we can use law of cosines. Be careful, don't assume that you can just take half of this angle to get the smaller piece of the angle. Once you know, if you happen to know, let's say, the bottom half of this angle, so the smaller one on the bottom side, it's true that it's going to be equal to the top half over here, but this and the top and the bottom of this are not necessarily the same. So don't assume that. Now, so using law of cosines, we want to solve for this side. We know that law of cosines, if you recall, is, I'm going to call this x. So we would say that x squared is equal to the squares of the other two sides. So 60 squared plus 40 squared minus 2 times 60 times 40 times cosine of the angle opposite where we started from. So it would be this angle, and we didn't find this angle yet. How do we get this angle? Well, this original angle back here was 40 degrees before we cut it in half. So, of course, this one's also 40 degrees over here before we cut it in half. And the parallelogram has a total of 360 degrees. So, 360 minus 40 minus 40, that's going to be 280. And then if we divide 280 in half, then we would be left with 140 here and here. So this angle is 140 degrees and is opposite that diagonal that we're solving for, so we're going to put cosine of 140. So this is just law of cosines, just like we did in section 8.2 here. And then we can solve this for x. You definitely want a calculator to help you with this step. Alright, so typing all this in, we've got, I'm trying to get it where you can see both at the same time if that's possible. Okay, so we've got 60 squared plus 40 squared minus 2 times 60 times 40 times cosine of 140. Make sure your calculator is in degrees. Okay, I got 8,877 and a decimal. Now I need to take the square root, so second square root, second answer. That gave me 94.2. I think they said round to the nearest tenth. So we got x equals 94.2, and that's it. The units were in pounds, so 94.2 pounds.